Hi everyone, very happy to introduce our work, D-Convexity, a unified differentiable convex shape prior via quasi-concavity for data-driven image segmentation. The main idea is simple. Many objects we segment in medical and natural images are convex or close to convex, but it is not easy to impose convexity inside a modern neural network. Our work revisits convexity from a functional point of view and turns it into a practical prior that can be integrated into neural networks. In segmentation, the network usually predicts a continuous mask U, and then we choose a threshold to get the final object. Classical convexity is a geometric constraint on that thresholded object. The problem is that the object depends on the chosen threshold. If we only check one threshold, the network may still produce holes, irregular boundaries, or non-convex shapes at other confidence levels. Our solution is to require every superlevel set of U to be convex. This is exactly quasi-concavity. Compared with concavity, quasi-concavity is weaker and more flexible, but it still guarantees that each superlevel set is convex. So we move from a hard thresholded geometry constraint to a functional prior on the whole mask. Once we view convexity as a quasi-concavity of U, we can derive different conditions depending on the smoothness of U. For the zero-order case, we only assume U is continuous. The condition says that every point on a line segment should have value no smaller than the weaker endpoint. For the first-order case, we use gradients. If one point has higher value than another point, then it should lie inside the supporting half space defined by the gradient. For the second-order case, we use the Hessian. Intuitively, along the tangent direction of each level set, the function should curve downward. In 2D, this gives us a compact formula, Q2 of x smaller than 0, which is very useful for implementation. A nice part of this framework is that it also explains many previous convex shape priors. Some methods use line segment or graph cut style constraints. These can be understood as zero-order convexity checks. Other methods use binary disk checks. These can be explained by our first-order supporting half-space condition. And level set or sign distance function methods often use curvature constraints. These naturally connect to our second-order condition. So instead of treating previous methods as separate ideas, quasi-concavity gives one unified view of them. For the zero-order condition, directly checking all line segments is too expensive, so we use a local midpoint convexification algorithm. The idea is, for a local pair of endpoints, look at their midpoint. If both endpoints have high values, then the midpoint should not be too low. So we lift the midpoint value to satisfy the local convexity rule. We repeat this over local neighborhoods until the mask stops changing. This gives a simple and intuitive way to convexify masks. For the first and second order cases, we turn the series into differentiable losses. The first order loss penalizes violations of the supporting half-space condition. The second order loss penalizes violations of the Hessian-based condition. Then we introduce CGPM, the convex gradient projection module. Given a raw network output, CGPM finds a nearby mask that better satisfies the convex prior. This can be viewed as an unrolled optimization step, so it can be integrated into modern segmentation networks. Here we show qualitative examples. The toy examples show how the 0, first, and second order priors gradually convexify non-convex shapes. The real segmentation examples show that our method produces more regular and shape-consistent masks compared with several baselines. The goal is not only to improve overlap metrics, but also to make the predicted shape more plausible. Quantitatively, we evaluate on multiple datasets, including ACDC, CASIA, Refugee, and RIM1R3. Across these datasets, the proposed method improves dice and IOU, and often reduces Hausdorff distance, which means the boundary becomes more accurate and more stable. The ablation study also shows that the convex prior is useful across different backbones, and the second-order condition gives the strongest overall improvement. To summarize, D-Convexity turns convex segmentation into quasi-concavity of the continuous mask function. This gives us 3 levels of theory: zero-order, first-order, and second-order conditions. It also unifies several previous convex shape priors under one framework. Most importantly, the resulting losses and CGPM module are differentiable and practical for modern neural segmentation networks. You can find the paper and code using the QR codes here. Thank you for listening and have a great day.